So let's talk about this fine-tuning. This is something we'd like to investigate with Lattice. It's the perfect tool. We can change quark masses and look at the nucleon-nucleon interaction to see what might be going on. And I know that with Raoul, you discussed scattering amplitudes, and you talked about unitarity and things in kind of a mathematical way. So we're going to apply that through an effective field theory for nucleons. So let me write this down. So the Lagrangian, effective Lagrangian for nucleons, if we assume that we're at energy scales much, much smaller than the pion mass. So this means that we can't produce pions. The only things that we have in our theory are nucleons. And I'm also going to look at a non-relativistic theory. So we have non-relativistic interacting nucleons. So the simplest thing that you can write down, we have our nucleon fields, which are fermions, so I denote them by the field psi. And hang on, there we go. Okay, this guy here, this is the non-relativistic inverse propagator. So it looks similar to what you might be used to, except that since we're non-relativistic, space and time happen differently here. But think of d tau as being like an energy and grad squared over 2m as being like momentum squared over 2m, which is what you would see for a non-relativistic theory. Okay, and then we want them to interact. So we give them a coupling. And this right here, this is a two nucleon interaction. And so diagrammatically, what that looks like is I have two nucleons coming in, they interact at a point, and the amplitude for that interaction is G naught, which is the coupling. Okay, so now we want to look at two nucleon scattering. So we can write down the form of the S matrix, which I assume you have seen before, although the normalizations might be slightly different because this is a non-relativistic theory. So this is the scattering matrix and the scattering amplitude. Again, this is probably a different normalization than you're used to because we're in a non-relativistic theory, but it still has roughly the same dependence. So this you should have seen before. The scattering amplitude depends inversely like p cotangent delta, where delta is the scattering phase shift minus IP. And then hopefully you guys remember the effective range expansion, where we assume that we are at low momenta. And by low momenta, we mean low compared to, say, the inverse size of the interaction. And that's just another way of saying that we're assuming the nucleons all interact via point-like interactions. So then this guy looks roughly like this. So it goes like -1 over A, where A is the scattering length. This sign here differs between nuclear physicists and particle physicists. It's one of those confusing things that is super annoying. I believe the minus sign, I am using the nuclear physicist convention, but we'll just call it my convention because that's what I'm going with. And then we have the second term, which is depends on R naught, the effective range, plus higher order terms, minus IP. Okay. All right, so we want to evaluate the scattering amplitude and look for bound states because that will tell us what the binding energy of this two nucleon system is. So we can do that diagrammatically. We know that the scattering amplitude looks like this first diagram that I wrote up here. So this is the tree level scattering. So time here runs from left to right. So two nucleons come in, they interact at this point, and then they scatter off. And since this is a non-relativistic theory, it turns out that the number of Feynman diagrams you can write down is actually very small. So another one that I can write down at a one loop order would be this guy. So here we have two interaction vertices, and then we have some integral that our loop calculation gives us. I'm not going to do that, but it's pretty straightforward to do. And then you can also have two loop ones. Yep, G naught, G naught, G naught. And then these two loops are identical. There's no momentum dependence in these vertices, and so the momenta that runs through this loop is totally independent of the momentum outside of it, which means that you can factorize these loops. And so in fact, you just get 2 powers of I naught, plus all other so-called bubble diagrams. Now, I said that this is a small number because it's a non-relativistic theory. So what that means is because time runs this way, that's a t, not a plus, and we have a non-relativistic theory, we can't have diagrams that look like this because we can't have particles that propagate backwards in time, or in other words, we can't have antiparticles because we're in a non-relativistic theory. So all diagrams like this go away. You won't have any, tadpole diagrams, anything like this that involves antiparticles we don't have. The only thing that these nucleons can do is come in, interact, and then scatter off. And so